Good evening, my dear NEET warriors. This is your Captain Shreyas, and we are on to the chapter of electromagnetic waves, chapter 8 of your 12th standard NCERT physics. And we are in the NCERT line by line series for all the NEET aspirants. Remember, this series is not just for reading through the NCERT, but also seeing the significance and the applications from the NEET point of view. So let's get started. Lots of cool things to learn about electromagnetic waves. They are really cool to actually visualize and see how they are used in different applications. It's a very short chapter, but there is almost like 99% chance that you will get one question from this. Best part, you need less time to get those marks. Exactly. So this is some chapter which you should definitely not leave. Hello Aru, hello Krishna, good evening, evening star. Welcome, my dear warriors. Time to begin with the class and let's start. And those of you who do not know me, well, my name is Captain Shreyas, your navigator, your guide in this ship which is going to go through these turbulent months of your NEET preparation, where you will need support, guidance, lectures, strategies, announcements, news, notifications, everything which you need. I am going to do it for you on this particular channel. This channel is your channel. Remember that this is called as a Vedantu NEET English channel. It's the best and the #1 channel for students who want to learn in English, especially all the students from South India, the metro cities, Northeast, and even students who are living abroad. Okay, thank you for subscribing. If you have not done that yet, do that right now, and also do not forget to like the video after subscribing. Right? Thank you so much for showing all your support. Good evening. All the warrior Pandus assembled. I am very good, Krishna. Actually, I'm not very good. I'm just good. Reason is I have slight bit of fever. I have popped in 2 dolos. That's what people do when they are feeling little bit under the weather. But hopefully, I should be fine by tonight or maybe tomorrow. Hi, good evening. Let's begin. So, hi Gokulnath. Now, this chapter deals with something called as electromagnetic waves. What is this electromagnetic wave, and where is it used? In fact, it is used everywhere. Even my mobile emits electromagnetic radiation. It also receives electromagnetic radiation. Forget that, even me right now, I am emitting electromagnetic waves and I am receiving electromagnetic waves everywhere. The light is there. Light is also electromagnetic wave. So electromagnetic waves are there completely around us, and we depend on it in many different ways. And right now, in this particular introduction part, you will see that we have so far considered direct current sources. These do not change the direction with time, but voltages and currents which change with time are very common, and they are used in our homes, offices, etc. like a sine function with time. Such a voltage which, oops, I think this is AC by mistake, this introduction. So sorry guys, this introduction was supposed to be changed. I'm not sure why it was not changed. So sorry. That introduction is of AC, my bad. Alright. So in this particular chapter, like I said, you will be learning about electromagnetic waves, the application and the wave theory behind it. And one of the main person to talk about electromagnetic waves was James Clerk Maxwell. I'll tell you one very interesting story. I don't know how many of you know this. Everybody wants to listen to a story. All right, let me tell you. J25, well, not problem-wise J25. Theory-wise, this should be enough. Yeah. Okay. So, long time back, it was Newton who said that light behaves like a particle. Light behaves like a particle. But on the other hand, there was a person called as Huygens, and Huygens said that light behaves like a wave. And to show that light behaves like a wave, in fact, there were many setups, or there were many experiments to prove it likewise. And one such was done by Young. So Young performed, and the name of the person is Young. It's not an adjective, it's a noun. So Young was Thomas Young. he performed an experiment to show that light behaves like a wave, but people thought, no, 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 how can you talk against Newton? It is wrong. So they thought something is wrong with these people only. So they believed, this is 200-300 years back, they thought light is a particle only. Even when Young proved it otherwise. Then there were other people like Fresnel and other scientists, okay, who proved that light is a wave. Still for the next couple of 100 years, people thought that something is wrong with these people. What Newton said only is correct. Light is a particle. Then what happens is, Maxwell comes into the play. Maxwell comes into the picture. Even before this, there were even more scientists. I have not mentioned all the names. All right. So Maxwell comes into the play, and he proves that light is a electromagnetic wave using some equations. So after some 100-200 years, people realize, oh, Newton was wrong. Actually, light was a wave. These people were correct. So that was how crazy things were back in history. But then there is always a party pooper, right? So to spoil the party, who came is basically Planck and Einstein. Einstein through photoelectric effect and Planck through the quantum theory proved that light is a particle, and the particle of light is called photon. And Einstein even won Nobel Prize for photoelectric effect, not for theory of relativity. So then people thought, what the hell? We thought Maxwell was correct. He disproved Newton. So was Newton right after all? Then people understood after all of this, listen, light has nothing but dual behavior or dual nature. Yes, dual nature. Sometimes it behaves like a wave, sometimes it behaves like a particle. And when I say it behaves like a particle or behaves like a wave, what exactly do I mean? See, when something is behaving like a particle, it has momentum. When it hits something, it applies a force. It makes its presence felt by the touch or that momentum or that impulse, right? So these are particle-like behaviors. But what is wave-like behavior? Wave-like behavior is where, you can say that it will get diffracted, refracted, reflected. These are properties of waves. So when a wave goes from one medium to another medium, it refracts. When a wave enters a small gap or a hole or around a corner, it will spread. That is called diffraction. All these properties were also shown by light. So that is why then it was concluded light has dual behavior. Like some of us have in the school. We are full mischievous. We are on our full excitement levels, and we are doing a lot of hangama masti. We are doing so much of fun. We are pulling each other's legs. But at home, very silent. So dual behavior. You might have seen some friends of yours at home, suddenly because of their parents or whatever reason, suddenly very quiet. You are only surprised. What is this? This is my friend. He's so quiet here. And then in the school, full masti, full on his or she's enjoying. So that is basically dual behavior of light. And what we talk about is Maxwell's electromagnetic wave theory. That is what we are going to talk about. And in that electromagnetic wave theory, there is one important concept called as displacement current and how he gets through it. And they have explained that displacement current concept and the modified Ampere's law. So you can see this is Ampere's law, and the total current is a sum of two different currents, and one of them current is called as the displacement current. All these things I will explain. And he modifies the Ampere's law into something like this, and he is then able to prove all of it. So what is exactly mentioned over here? Let me explain, guys. Let me explain. Okay, in the first few parts, because a lot of people do not really understand it. If you recollect Ampere's law, then if you have a wire which carries some, if you have a wire which basically carries some current, if you have a wire which basically carries some current, and then you take a loop across it, you take a loop across it, that loop is basically a path. That loop is basically a path. So you go around this particular path like this. This is called as an Amperian path, which is basically a closed path. And along that path, you will start seeing some magnetic fields. You will start seeing some magnetic fields, maybe like this. And these magnetic fields, if you integrate it with respect to the small path lengths by taking a dot product, and you cover that entire closed path, that's why cyclic integral, what you get on the right hand side is permeability into the current which has been enclosed, into the current which has been enclosed. This is exactly what your Ampere's law was. I hope you remember it. It's a small recap of that. Dot product of magnetic field with the path length around that loop is permeability into the current which passes through that particular section. That is what this is all about. So when I say passes through the section, what do I exactly mean? If you visualize a thin film which is being formed by that loop, imagine you take a wire frame or you take some object and you dip it in a soapy liquid, a film is formed, soapy film is formed. So imagine this to be like that soapy film, and this particular current is piercing that soapy film over here, is piercing that soapy film here. So then that current is called as the enclosed current. But then, is it necessary the soapy film has to be a flat surface? The answer is no. Imagine there is a wire like this carrying current. There is a wire like this carrying current. There is a wire like this carrying current. In all the three cases, let me take my Ampere's loop law. All right. Okay. In the first case, let my film be like this. So the current pierces it right over here before coming out from behind of it. In the next case, what if my soapy film is slightly more curved? What do I mean by that? Observe this carefully. Slightly like this, or what if it is like this? Are you able to visualize that curviness? Are you able to visualize that curviness? That solid shading is basically the inside of it. So the wire will go through it like this. It might pierce through it over here. The wire might go through it. It is not piercing here. It is not even piercing at this structure for this particular surface, because the wire abruptly is ending over here. The wire is abruptly ending over here maybe. So now, if you look at all these three diagrams, is the enclosed current same in all three of them or not? Are you saying that the enclosed current will be same or will it be different? If you notice over here, in this particular structure, when the film is flat, the enclosed current is basically I only. Here, it might not intersect this part. Well, it is intersecting this curved part somewhere here. Fair enough. Still, that enclosed current is I. But imagine if this was like a capacitor. Imagine this was like a capacitor which is there, or some wire is abruptly ending over here. It is not exactly intersecting at this point. Even if the current is I, then the problem is the enclosed current will not be I, because it is not piercing through it. there is no piercing, there is not intersecting that surface. It is not intersecting or cutting through it. It is not intersecting or cutting through that particular surface. So then what exactly is my definition of enclosed current? What exactly is something wrong with it? The answer is nothing is wrong with my definition of enclosed current. Enclosed current is defined in such a way that if you take that Amperian path, you make a film, whether it is flat or curved, that wire must intersect it somewhere or the other. That wire must intersect it somewhere or the other, either here or over here or at that flat surface, somewhere or the other it should intersect. But if it is not, then what to do? If it is not intersecting, then what to do? Here comes the solution. Well, observe this carefully. Observe this carefully. Imagine there is a wire which carries current. Imagine there is a capacitor, something like this. This is a capacitor. This is a capacitor. And somebody has taken an Amperian loop like this. Somebody has taken an Amperian loop like this. And our film which is there, it goes like this. It goes like this. Now the problem is this wire is not intersecting only that surface. So if somebody applied Ampere's loop law and said cyclic integral B dot dl, B being B only, is equal to mu naught into I enclosed. The problem with this approach is that at all these points you still have magnetic field as before. The magnetic field is still there. The magnetic field is as it is and should not depend, and it should not depend on the choice of the Amperian loop or its curvature. Curvature as in whether it was flat, whether it was curved like this. Whether it was flat, whether it was curved, whether it was more curved. It should not depend on that. It's like saying, because I changed the sign convention, so my velocity in kinematic equations is 100 meters per second instead of 20 meters per second. That should never happen. If the car was moving at 20 meters per second, no matter what origin you take, no matter which direction you take positive, you should always get the car's speed as 20 meters per second. It should not depend only on those references or those origins or what is positive and negative. Same way, this magnetic field around this region, why should it depend on whether it is flat or curved or not? Because this was just an Ampere's loop law which was just made up. So that is the reason why we have to think a little bit differently. And when you take a curved surface like this, then you might be wondering, sir, there is no enclosed current in this case. Obviously, this is a big fat zero. So how is it that the RHS is 0 and the LHS is not a 0? Not a 0. How is this possible? This cannot happen. The LHS has some magnetic field, but RHS has 0 term. So something is not matching over here. So definitely our LHS is not matching the RHS. RHS is 0 and LHS is obviously not 0. So to overcome this trouble, they finally understood where we were going wrong. The place where we are going wrong is that there is a missing term in the Ampere's loop law equation. Yes, there is a missing term in the Ampere's loop law equation, and the missing term is as follows: plus something called ID. Something called ID. This is basically called as your displacement current. Displacement current. And this displacement current is not zero. This particular displacement current is not zero. And in that peculiar scenario, you will see LHS will match the RHS. I'll explain to you what is this displacement current, but for now, understand there was a missing term because of which we never got LHS equal to RHS. So, what is this displacement current? This displacement current is due to changing electric fields. Changing electric fields, which creates magnetic field, Very interesting thing about displacement current. Observe this, what I'm trying to say. If you have just taken a charge, obviously it will create some electric field around it. It will definitely create some electric field around it. But let's say somebody, moves this charge from here to here. Somebody moves this charge from here to here. In this process, what will happen is that at any point, if you see the electric field at this point, due to this charge before was here, but due to this charge after some time will be here. This was electric field initially, this was electric field finally. So definitely there is a change in the electric field. This change in the electric field induces, that means it creates a magnetic field. This creates a magnetic field. But do you remember, we always have spoken that magnetic fields are created by whom? Magnetic fields are usually created by whom, guys? Magnetic fields are created by currents. Magnetic fields are created by currents. But here magnetic field is created by electric field. So we define a term called as displacement current. A displacement current is that physical current which would produce the same magnetic field as the changing electric field. So over here, if there was some kind of magnetic field which was created, that magnetic field which is created by the same current by a physical wire, that is then called as displacement current. It is not because of an actual current, but it is like the current which will produce the same magnetic field. I hope this is clear. This is like a substitute. You can think of it like a alternative, like a substitute. It's that alternate current, that substitute current, that current physically which produces the same field, magnetic field, that current is called as the displacement current. I hope this is absolutely clear. Hello Umesh, welcome. Yes. Is this part understood, everyone? So displacement current is due to changing electric fields which creates the magnetic field, and the value it is basically nothing but that current which produces the same magnetic field over here. So now our equation looks fine. Okay, there is displacement current, but your question will be, sir, what is that value of that displacement current? We can find that out very easily. It is not that big a deal, because see, the thing is LHS has not changed. So basically, LHS has not changed. So basically, if you see over here, if you take a flat surface, then the enclosed current would have been I. But if you take a curved surface, then the displacement current should be I. This, understand, in the first case, if you take a flat surface, nothing is passing through the empty space between the capacitor, then the displacement current will be 0. But if you take a curved surface, then the enclosed current will be 0, but the displacement current will be I. Why? Because LHS is same, magnetic field did not change, so RHS should not change. So I plus 0 or 0 plus I, one and the same thing. I plus 0 or 0 plus I, one and the same thing. Keep that in mind, so that our LHS is not affected. Keep this in mind. So lot of times you will see this. Is the enclosed current value the same as the displacement current value? Yes, you can see that it is the same. But when this is there, this is not there. When this is not there, this is there. They substitute. That's what I told. It's like an alternative. It substitutes the enclosed current. Okay. So what is this value of this displacement current? How do I find it? This is also I. This is also I. So therefore, ID will be equal to I enclosed. I enclosed is basically that I, which is also dq by dt, rate of flow of charge. What is charge? What is charge? Q is CV. So I can write it as capacitance into voltage divided by dt. Okay. Can I do something with this? Yes, capacitance can be taken outside and we will have dV by dt. Capacitance is epsilon naught A by D. What is voltage dV by dt? Can I do something with this? Yes, I think I can do something with it. Think about it. Think about it. Can I do something with the voltage? Voltage is nothing but voltage. Well, electric field was dV by dx. Electric field was dV by dx. So dV will be EdX. dV will be EdX. So think of it like that. Yes. So that is one thing I can do. So instead of this, I can write it as electric field into that distance. Now electric field into that distance will be exactly this d, you can say. That distance will be basically d over here, and actually over here that d will come instead of dv. So think of it like this. Think of it like this. This voltage is nothing but, I'll just rewrite it again before. This voltage is nothing but electric field into distance. Electric field into distance. Don't get confused with this d and this d. This is derivative. This is distance between the plates of the capacitor. Okay. So what will happen is that d, if I take it outside, it will become epsilon naught A by d. That d is outside, and then we have basically dE by dt. This d and this d got cancelled. Now take this area inside, it will become epsilon naught d by dt of EA. Now what is electric field into area? What is electric field into area? Electric field into area is the electric flux. So it will be d phi of electric flux. Yes, by dt. So therefore the displacement current is permittivity into rate of change of electric flux. Permittivity into rate of change of electric flux. So that is the derivation for that, and hence I usually will write it over here. This particular displacement current is nothing but permittivity into rate of change of electric flux. This is permittivity into rate of change of electric flux. Electric flux, very, very important. Rate of change of electric flux. Sometimes this enclosed current, sometimes this particular enclosed current is also called as, this particular enclosed current is also called as the actual current, which is therefore called as conduction current. Conduction current. is the actual current. It is the due to the flow of charges. So it is due to the flow of charges, whereas the displacement current is due to changing electric field. It is not due to charges, it is due to how electric field is changing. So there are two different things. So enclosed current is your actual current, conduction current, and displacement current is epsilon naught d phi by dt. So this becomes your modified law for Ampere. Earlier our Ampere's law was like this. So now it has been modified. It has been modified by adding one extra term over here and making the entire equation correct, no matter how curved or flat your surface is while measuring enclosed current. So now with this, what we have done is we have modified Ampere's law. So the modified Ampere's law will look like this. Modified Ampere's law will look something like this. Integration of magnetic field with respect to the path length is mu naught into the actual conduction current plus permittivity into rate of change of electric flux. This is your modified Ampere's law. Then Maxwell wrote the Gauss's law also, the Gauss law in electrostatics. Gauss law in electrostatics, which looked very similar to this. Instead of magnetic field, you had electric field. Instead of length, you had the area vector. This was the electric flux, the total electric flux of the closed surface. This was always the charge which is inside or enclosed by permittivity. Then there is also Gauss law in magnetism. Gauss's law in magnetism, if you remember, and that was integration of magnetic field with area, which is the total magnetic flux on a closed surface, is always going to be 0. We have seen this in the chapter of magnetism. And the final law was your Faraday and Lenz's law. Faraday and Lenz statement, which said that the EMF which is induced is negative rate of change of the magnetic flux. This is magnetic flux, how quickly the magnetic flux changes. And this EMF induced in a loop, can be also written down as integration of dV, V being the voltage, but it's a loop. That's why this cyclic integral, it's a loop, right? So closed integral of the voltage in that loop is minus d phi by dt. So these equations are there in your electromagnetism, and these four equations alone define the entire electromagnetism unit. And this is exactly what Maxwell used. That's why they are also called as Maxwell's equations. He combined these equations together, and then he was able to prove using these equations light is an electromagnetic wave. Right now, I know looking at these equations, it looks like as if a cockroach was dipped in some yellow and orange ink and it was asked to run over this board randomly. But it is not like that. These equations actually have a lot of meaning. We have seen this. This is the substitute for Coulomb's law. You can derive anything based on this in electrostatics. This was for magnetic field due to currents and due to changing electric fields. This is for just magnets, how the magnetic field lines behave. And this is how when magnets, move around here and there, producing some changes, how is that electricity created? The entire of electromagnetism physics is right on this particular board. And he said that electric and magnetic theories are not separate, rather they are interlinked with each other, rather they have some common connection between them. And you can see one side you have electrostatics, voltage, other side you have magnetism. One side you have electrostatics, other side you have magnetism. So they are interlinked to each other. That's what Maxwell was able to say. I hope this is absolutely clear. So this is what is given over here, right? Exactly the same thing. Maxwell's equations. Maxwell's equation. So he was able to say that, of this existence of electromagnetic waves, which we'll discuss right now. And all these equations, he was able to prove that light is an electromagnetic wave. Cool. So that is what is there in the starting part of the chapter. All right. So, sir, can we get some questions on this? Yes, you might get some very laddu-paddu questions on this. Something like, say for example, if electric field is 5t square, area is 2 meter square. This is volt per meter. Can you find the displacement current? Can you find the displacement current? How do you solve this particular question? Let's go by the pure definition of displacement current and the formula. The displacement current is permittivity into rate of change of the electric flux. But wait a minute. Electric flux, I think I already know the formula for electric flux. It's nothing but electric field into area. Oh, do I know the electric field? Yes, why not? It is right over here, guys. It is right over here. So derivative of basically 5t square. Do I know the area? Yes, why not? It is basically 2. Okay, perfect. So 5 2s are 10. So it will basically become 10 times of E naught. And I'm just left with the derivative of t square. Derivative of t square is nothing but 2 times of t. 10 into 2 is 20. So 20 epsilon naught t is nothing but the displacement current. If you want, you can substitute the value of epsilon, which is 8.85 10 to the power minus 12, okay, and multiply it with 20. And if time is given, you can multiply with time. You will get the answer for the displacement current. I hope this is clear. Yes. Oops. Cockroaches. I don't like in the chats. I get scared, especially when they fly. Okay. So very straightforward, guys. And let's go to the main topic, which is electromagnetic waves. So how do electromagnetic waves look like? What is their equations and other parameters? In the NCERT, the way they have presented is so boring. I don't like it. So let's just have a look at 𝐂𝐤𝐤's diagrams and 𝐂𝐤𝐤's way of explaining, of course. So let me just block few things over here, like you have the electromagnetic wave equations, K definition. Okay. You will also see E and D are perpendicular. Okay. All these things, omega is 1 by this equation, all these things are there. And then there are problems. So let me explain this to you. Basically, imagine light to go in this particular way. This is the direction in which light is going. So this is light ray. If you have seen ray optics, you show rays of light, right? So this is the light ray. This is the direction in which the light is going. What is this c, you might ask? This c is nothing but the speed of light. This is nothing but the speed of light. And we know in vacuum it is 3 into 10 to the power 8 meters per second. When any electromagnetic wave, meaning light, X-rays, gamma rays, Bluetooth, Wi-Fi, infrared, ultraviolet, red color, blue color, white light, anything, thermal radiation, long radio waves, short radio waves, microwaves, all these waves, when they travel, they have very similar characteristics. If they are traveling like this, you will see probably the electric field going like this, up and down. and you will see the magnetic field going left and right. This one is magnetic field. This one is electric field. You will see electric field, magnetic field, and the velocity of light. All three of them are mutually perpendicular to each other. Mutually perpendicular to each other. This is how an electro, yellow one, magnetic, the green one, electromagnetic waves propagate. If somebody sees it from behind, imagine there was an observer, or maybe from the front also, doesn't matter. Imagine somebody had to see this from behind. What would that person exactly notice? That person would see that the electric field is continuously changing up and down. It's continuously going up and down, and the magnetic field is continuously changing left and right, and the light ray is going away from him, something like this. The light ray is going something like this. If the electric field at any instant, is like this, then the magnetic field at that instant will be like this. And if the electric field is downwards, then the magnetic field will be towards the left side. How do I know magnetic field is right only when electric field is up and not towards the left side? There is a simple rule for that, and that is electric field and magnetic field, if they are cross-producted with each other, the vector that you get is always going to be parallel to the velocity of the light. Notice electric field is on the top, take the right hand, cross-producted with magnetic field, the thumb goes inside, so that's exactly the direction of the velocity of the light. Here also, if I do electric field cross magnetic field, the thumb goes exactly here, exactly what I am expecting it to do. How does it actually look like? For that I have created, I'm using a simulation over here. I can see electric fields or magnetic fields. Look at that. See how electric field is continuously changing up and down like a wave. This is electric wave. Similarly, look at this magnetic wave. See how the electromagnetic wave is traveling in this direction. Now let's see both of them together. One is in one plane, other is in perpendicular plane, and the wave is traveling in the third direction, mutually perpendicular. Don't worry, Krishna, chumma kidding, man. Yes. Now, how will it look like if they move? We'll see that, but let me show you the planes. Can you see the electric field wave? Can you see the magnetic field wave? Can you see that this green plane is perpendicular to the red plane of the magnetic field? Correct? Now let's see what happens if they start moving. See, this is how they go. So if you are standing at one point, suddenly the electric field is increasing, increasing. Magnetic field increasing, decreasing. So at any given point, the magnetic field and the electric field will keep changing. How quickly they change gives me the frequency, the distance between two crests or two troughs. Gives me the wavelength of that wave. So when you are seeing light, exactly this is what is entering your eye. Electric and magnetic fields are entering your eye. When you see beautiful colors, they are just electromagnetic waves of different wavelengths. Yes, they are of different wavelengths. That's all. Is this visualization absolutely clear? Everybody with me? Yep. Cool. Beautiful simulation, right? Amazing it is. Yes. Not just that, there are some more things that you should obviously know about this. this electric field has an amplitude, let's say E0, then the electric field's wave equation is given by E0 sine or cos, anything you can use, sine or cos, and then you have kx minus omega t. Similarly, if the magnetic field has a maximum value of B0, that is the amplitude of the magnetic wave, so the magnetic field is given by B0. If you use sine here, use sine. If you use cos over here. Doesn't matter what you use, but this is how it is. If you put kx here also, minus omega t. That's it. It can be plus also. So I'll put minus and plus both, depending on the direction of which it is moving. What is this E0 and what is this B0? E0 is nothing but electric field's amplitude, the maximum value of the electric field. Any wave has an amplitude, right? So same thing. So this is nothing but magnitude of the magnetic field's maximum value, or you can say magnetic field's amplitude. Magnetic field's amplitude. What is E and B? E and B are the current values of the electric field and the magnetic field. Meaning, say for example, you are somewhere over here and let's say, you are interested what is the magnetic field at this location, what is the electric field at this location, and this point is at some distance from the origin. So that distance is basically x. This was, let's say, our origin. X is how far you are from the origin. So at that location, what is the instantaneous values? So what are these? These are basically instant values of the electric field and the magnetic field. What is this K? What is this omega and all these things? We'll come to that as well. Don't worry. Yes, what is this K and all these other things? So, yes, this K is 2 pi by lambda, which is also called angular wave number. And the unit of that is how many radians are there in a meter. K is 2 pi by lambda, lambda being the wavelength. Lambda is the wavelength. Yes, is the wavelength. Correct. Is the wavelength. What is omega then? What is basically omega then? Omega is 2 pi by t, which is also 2 pi into f. That is called as angular, we have seen this word, frequency. Angular frequency. Unit is radian per second. What is this f? F is just called frequency, not angular frequency. Angular frequency is radian per second. Frequency is just per second. Frequency is just how quickly it goes up and down. That is what these terms are. Apart from that, you should know one more thing, and that is, if you use a plus sign, remember it is moving along negative x-axis, and if you use a negative sign over here, that means the wave is going along positive direction of the x-axis. So it is exactly opposite. If it is negative, that means the wave is going towards the positive side. If it is positive, then the wave is going along the negative side. So it is always opposite, the signs. Be careful about it. Next important thing which you should know. Over here. If you divide E with B, if you divide electric field with magnetic field, it is as good as saying you are dividing electric field amplitude with magnetic field amplitude. Both of them will be in the obviously same ratio. If I divide E with B, E naught with B naught, same thing, because this and this will get cancelled. This ratio is exactly what is going to give me the speed of light. This is exactly what is going to give me the speed of light, which is also f times of lambda, frequency into wavelength, which is also omega by k, angular frequency by angular wave number, which is also 1 by permeability and permittivity. So what is mu over here? This is permeability, not refractive index, permeability, and this one over here is basically permittivity. Yes, permeability into permittivity. All these things will give me the same answer. This you already knew. Speed of any wave is frequency into wavelength, also omega by k from the chapter of waves. E by B, E naught by B naught, one and the same thing. This is something which you are learning new, either this or this. Keep this in mind. Also, you need to know one more thing. The amount of electrical energy per unit volume. If you take 1 meter cube of space, how much electrical energy it is carrying will be exactly equal to how much magnetic energy it carries, per unit volume. Do we already know the formula for electrical and magnetic energy? I think we already know. Electric energy per unit volume is given by half epsilon naught E square, and magnetic energy per unit volume is half B square by mu naught. Half B square by mu naught. Half cancels, and if you notice what happens over here is that you get a very interesting thing. On the top you have electric field square. Take this permittivity below. Magnetic field you take it below over here, and this mu naught keep it as it is over here. In the next step, what will happen is, guys, a very interesting thing. This will be, if you take root on both sides, this will be electric field, this will be magnetic field, and on the right hand side what you will have is 1 by root of mu naught and epsilon naught, exactly what you got over here. That's how you prove E by B is exactly this. That's how you prove electric field by magnetic field is 1 by permeability into permittivity of that medium. Correct. And also keep in mind one more thing, and that is the total energy. The total energy will be the sum of magnetic and electrical energy. So whatever electric energy per unit volume or magnetic energy per unit volume you are finding out, that will be basically half of the total energy of the electromagnetic wave per unit volume. I hope this is absolutely clear. Okay, total energy will be electric and magnetic energy sum. So electric will be half of total energy, magnetic will also be half of the total, because both of them are present in equal amounts. So these are the only formulas and the things which you should know regarding electromagnetic waves. And then there are some questions on it. Let's have a look at the questions, my dear warriors. Okay, see, example 8.1. A plane electromagnetic wave of some frequency travels in space in x direction. At a particular point, electric field is 6.3 j-cap. What is magnetic field at that point? Okay. In this particular question, electric field is given, magnetic field is asked. Oh, thank you for reminding me to have water. Thank you, guys. We know electric field by magnetic field is speed of light. So magnetic field is electric field by speed of light. Electric field is 6.3 volts per meter, and speed of light we already know is 3 into 10 to the power 8 meters per second. So dividing both of them, that's exactly what they have done. 6.3 divided by 3 into 10 to the power 8, they get the value of magnetic field as 2.1 into 10 to the power negative 8 Tesla. So we found the magnitude of the magnetic field. But that's not all, we have to also find the direction of it. So I have an idea. See, where is the electric field direction? Electric field is in J cap. Electric field is basically in J cap direction. Where is the velocity of the light? Electromagnetic wave is going in X direction. So the velocity of the light is basically in the I cap direction. And we know magnetic field should be such that the electric field crossed with the magnetic field should be parallel to the velocity of light. Oh, so J cross something should give me I. J cross something should give me I. J cross obviously K cap. J cross basically K cap. Think about it. If this is K cap and if this is J cap, J cross K, what does it give you? It basically gives you nothing but I cap. So hence magnetic field must be along the K cap direction. So yes, the answer is 2.1 10 to the power minus 8, but in the K cap direction. Okay, so this property I have used over here. I just gave it to you. E cross B is parallel to C. This is what you have used. Okay, in this particular example, you will see many questions on that as well. Next question. The magnetic field is given by this 2 10 to the power negative 7 sine 0.5 10 to the power 3x plus 1.5 10 to the power 11, I think so, 11. Okay, T. What is the wavelength and frequency? Write an expression for the electric field. Okay, let's do it step by step. First, let's find what is the wavelength and frequency. Compare this equation with B is equal to B naught sine, okay, kx plus omega t. The moment you compare, you will understand B naught is 2 into 10 to the power negative 7. K is nothing but 0.5 into 10 to the power 3. Omega is nothing but 1.5 10 to the power 11. So immediately B naught is this is basically K, and this is basically omega. So now what we can do, K formula we know. What is the formula for K, guys? I had given you. K is nothing but 2 pi. K is nothing but 2 pi divided by lambda. So therefore lambda will be 2 pi, will be nothing but 2 pi divided by this number, which is 0.5 10 to the power 3. That's it. So 0.5 is half, 2 2s are 4, so it will become 4, it will just become 4 pi by or into 10 to the power negative 3 meters. So lambda is that many meters, which comes out to be 1.26 centimeters. Okay, so that is how you find lambda. Similarly, you can find frequency, because this is omega. Omega is nothing but 2 pi. Omega is nothing but 2 pi into f. Therefore, frequency will be 1.5 10 to the power 11 divided by 2 pi. That's it. So from this you will get the frequency, and they have got the answer as 23.23. What is happening to my board? 23.9 into 10 to the power 9 hertz. Now 10 to the power 9 is a giga. 10 to the power 9 is basically a giga. Yes, that's how you do this. Alright, so this is also done. Now the first part was done. First part is taken care of. Let's go to the second part. Write the expression for electric field. See, electric field equation should look exactly similar, just that here you will have E naught and here you will have sine kx plus omega t. Omega I know, k I know, E naught I don't know. So what do I do for E naught? There is a simple trick. Because I know electric field by magnetic field is C, therefore E0 by B0 is also C. So E0 is C times of B0. Speed of light 3 into 10 to the power 8. Magnetic field's amplitude 2 into 10 to the power negative 7. 3 2s are 6 and you will have basically 60. So 60 volts per meter. 60 volts per meter is basically E0. Therefore, E will be, instead of E0, I will put 60 sine K value already known, 0.5 into 10 to the power 3x, omega value already known, 1.5 10 to the power 11 into time. That is the answer. That is exactly what they have done. Is this clear, my dear warriors, how to do this question? All right, everybody with me? Very, very straightforward. Great. Awesome. So these are the kind of questions you can expect, and then we talk about the electromagnetic spectrum. It's a very important thing you should know about electromagnetic spectrum. Now, although this diagram is not so colorful, maybe I can get the diagram of electromagnetic spectrum. To show you what I exactly mean. Okay, this looks like a good diagram. This is also fine. Look at this. This is a beautiful diagram to explain you what is electromagnetic spectrum. See, you should realize by now from all these discussions that since speed is equal to frequency into wavelength, and all of the electromagnetic waves have the same speed in the same medium, in a given medium, all of them have the same speed, which means if something has very low frequency, it will have very high wavelength. Whereas something which has very high frequency, like this, will have very short wavelength. I hope this is absolutely clear. But in 1 second, if it has traveled 3 lakh kilometers, even this will travel exactly 3 lakh kilometers. The distance that they travel is the same, the wavelengths could be different, frequencies could be different. So something is oscillating very quick, the wavelength will be very small. Something is oscillating very slowly, the wavelength will be very large. They are both inversely related to each other. So, different waves have different wavelengths, and their usages, their phenomena, their applications, how they are generated, where do you see it, all these things are also going to be different. Like obviously blue color is different from yellow color, is different from infrared, is different from anything else. What you see around you is only this much. It's a small portion of all the possibilities in the universe. You can have a wavelength of 1000 kilometers also. That's called as a long radio wave. You can have wavelengths of the size of buildings, earths, few hundred meters, huge wavelengths. They are called as long radio waves. That's what you will see over here. Long radio waves, their wavelengths is in tens and very, very high powers of 10. You can make the wavelength shorter, it becomes a short radio wave. You can make it even shorter, it becomes a microwave, meaning few centimeters or millimeters. If the wavelength is a few millimeter, then it becomes like a microwave. You make it even shorter, you take it to few nanometers. In the range of nanometers, you go to infrared. You make it even shorter, it becomes red. Then you have orange, yellow, green, then blue, violet. All these colors will come. You make it even shorter, it becomes ultraviolet. Ultraviolet, yes, it's going to be very, very small. It will be very close to a few Armstrongs. Yes, it will go to a few Armstrongs. Then you go to X-ray, it will go to even lesser than an Armstrong or in the range of Armstrongs. And you go even smaller, it goes to femto, FM, 10 to the power negative 15th of a meter. And you go even smaller, you go to cosmic rays. It is not shown here, but that is also there when you go to very, very small wavelengths. If you talk about frequency, this is the highest frequency because the wavelength is small. Here, the frequency is very less because the wavelength is very large. So you can see one goes up, the other goes down, this goes down, the other goes up. Inversely related to each other. Is the electromagnetic spectrum clear to you? What you say is only this part. This is called as the visible spectrum. These rays, you can't see them. These rays, you can't see them. Just because you can't see them does not mean they do not exist. This range is from 400 nanometer to 700 nanometer. Now, who is 400, who is 700? I'll tell you that also. This is roughly 400 nanometers and the red wavelength is around 700 nanometers. That's such a small range in the world and the universe of possibilities. So you now know you should definitely have some kind of FOMO because you are really missing out on so many wavelengths which are around you. It's just that you can't see. Right now there are Bluetooth, Wi-Fi, radio waves around you, but it's just that you can't see them. But if you could see them, they would not look like blue or red or yellow. It's just that our brain just doesn't know it because we have never experienced it or not even capable of experiencing it. So understand, it's like talking about the Vibgyor colors to a blind person. No matter how much you sit and explain to a blind person what a violet color or red or green or orange or magenta is, they will never understand. But same thing, you apply it for yourself. So you are also technically blind to all these colors. So no matter how much anybody, even God comes and explains to you, you will not be able to understand it. Only a person with higher abilities or some divine person will be able to see all these colors. Understand that. But they have a lot of applications and they can be detected and generated in different ways. And that is what is given in NCERT last few lines, like radio waves. Radio waves, very low frequency. What do you use radio waves for? You use it for Earth to satellite communication, controlling some remote objects. You want to control a spaceship or you want to control some drone. They are typically using radio waves. Your AM, FM radio stations, which you have in your car, stereo system, radio stations, they also use that. Ham radio, walkie-talkies, all these things use radio waves. They usually have an antenna in them and they have an antenna in which the electricity keeps changing back and forth, and that produces changing, fluctuating electric fields which generates electromagnetic waves and acts like a transmitter. You can also receive those signals. Microwaves. Well, microwaves, the name comes from microwave oven again. You can see actually the microwave oven name comes from microwaves. So microwaves are used in microwave ovens. They are very short wavelengths, and the best part is they are used for speed guns. You must have seen some police person is standing on the side of the road with some object, and what is he doing? He is not firing anything. That is called as a speed gun, meaning it can detect how fast the vehicle is moving. So if you are over speeding, then you will get to know, the police person will get to know using that speed gun. That speed gun emits microwaves. It reflects from the vehicle and comes back. So it uses some it uses some electromagnetic phenomena, and it will basically be able to detect the speeds. The same microwaves are also used to detect the speed of a ball. You might have seen in cricket or tennis tournaments, they detect the speed of the ball. How are they able to detect it? Using microwave technology. Microwave technology, the wavelength is very much similar and frequency is very much similar to the sizes and the resonant frequency of water molecules. So resonance is a phenomena when the frequency matches, my frequency matching with your frequency, you will dance, you will be like, yes sir, I'm able to understand everything. Same way, water molecules frequency matches with the frequency of the microwave, they will love it, they will say yes, I'm loving it, just like McDonald's, and they will be like dancing. Once they start dancing, they vibrate, they will have thermal energy, and once they have thermal energy means they will get heated up. So that's why inside a microwave oven you will see the water molecules get excited due to resonant frequency and they get heated up, thereby cooking your food. But it does not affect the plastic or the ceramic because their frequencies are way different than the microwave frequencies. Alright, so that is what it is. Next, you have infrared. Infrared is basically, you know, they're everywhere around us. We humans also emit infrared waves. Yes, just that you can't see it. So that's why soldiers and during spy missions they use infrared goggles, because if it is dark you can't see anything, but we humans emit infrared. So if you have infrared vision night cameras, you can see the person in the dark. In fact, some of the animals hunt their predator using infrared rays. Example, snakes and some rodents, I think they see, even dogs, they can see infrared rays. That means they have more capability than humans, so they can see something beyond the visible spectrum. They can see slightly beyond the visible spectrum. Those rays which we are blind to, they are able to detect and sense them. Alright, but apart from that, infrared rays are also called as heat waves, and this is because the water molecules present in most materials absorb the infrared waves, and after absorption their thermal motion increases, they heat up and the surroundings. Infrared lamps are also used in physical therapy and also plays a role in maintaining Earth's warmth and average temperature throughout the Earth using greenhouse effect. So greenhouse effect is related to infrared rays because infrared rays can be absorbed by water very easily. Yes, so they can also act like thermal waves, thereby heating up the water and thereby, you know, participating in the greenhouse effect of the Earth. Yep. Your TV remote, even your AC remote, my AC remote right now, it has something over here. It uses infrared rays to communicate with the sensor on that AC or even your TV remote. Visible rays is the ones which you see, your rainbow, your colors, your paintings, human color, trees, object, everything around us is sensed by visible rays and we can see it very, very easily. Okay. Oh, so they have given an example. Snakes can detect infrared waves and the visible ranges. In fact, many insects can also extend into ultraviolet. So I don't know whom to blame. Imagine if we were able to see infrared and ultraviolet, then we could see people in the dark. So even if the electricity goes, it will be okay. We can even be sensitive to ultraviolet then. But thankfully we are not. That's why we use ultraviolet rays. You might have seen ultraviolet rays are used to repel some insects. In some hotels and restaurants, they have some violetish thing. What is that? Those are basically bulbs which emit ultraviolet rays which attract those insects and they get cling to it, and when they come close, there is an electric shock which is given and those insects will die. So ultraviolet rays which are detected by many insects, that is the application of it. So many things. Ultraviolet rays is also dangerous for human beings if you are exposed for a long time. So there is an ozone layer above the Earth which protects the harmful ultraviolet rays into reaching the Earth. The ozone, O3 molecules, they absorb those ultraviolet rays. But if the ozone layer finishes, then we are doomed because then we will be getting exposed to those ultraviolet rays. Yes. And yeah, that is what has been mentioned. Ultraviolet rays are damaging to our eyes. That's why welding applications, you will see they hold one glass when they are welding. Two metals have to be joined. Sparks come out at that welding machine. You cannot see those rays directly. You should not see those rays directly because they are harmful to your eyes. So that's why they use a welder's glass which absorbs those, ultraviolet rays. So all these applications, please read it properly, guys. I'm explaining all the interesting things over here so that when you read it, you will immediately relate. Yes, sir told me this. And in the exam also, these applications come. X-rays, they are very small in Armstrong region, Armstrong wavelength. and they are very energetic because of the low wavelength, high frequency. And these X-rays are used to detect fractures in some structures, fracture in bones, to detect crystal lattice structure of atoms, how that, you might have studied in solids, I don't know whether it's deleted now in chemistry, how that solids are formed, is it body centered, face centered, those things. So what is the size of the crystal? All those things are being detected using X-rays. But X-rays for a long time can be damaging to your muscles and skin. So you should be aware. That's why they say you should not keep on taking X-rays just chumma for time pass. Gamma rays. Gamma rays are even more energetic, high frequency, very small wavelength. Gamma rays are usually, going to come out from your nuclear explosions, nuclear fusions, those kind of things. Usually it comes through radiation, radioactive materials like uranium, thorium, all this, plutonium. They emit radiation, and those radiations are in the gamma ray range. They are extremely energetic. That means they will immediately burn you, and if you expose yourself for a few minutes or sometimes even few seconds, depending on the amount of the radiation, you might even die by radiation poisoning. That's what happened in Chernobyl and so many other nuclear disaster events. Also, it can be sometimes useful, wherein you want to destroy some unwanted cells, like treating cancer. So that's where gamma rays are used. Yes, gamma rays are used for even treating cancer. So their wavelengths, how they are produced, how they are detected, just remember this table. Very rarely, they have not asked till now, but in case they ask it, you should just have an idea of it. That is exactly what is there in this particular chapter. Like I said, it's a sweet, simple chapter. Read all the applications, know the complete visible, ultraviolet, everything about the electromagnetic spectrum. The formulas I have already given you, displacement current. These are the only things which are there and important in this particular chapter, guys. Okay, so that's a sweet, simple chapter, but which will fetch you 4 marks, now 99% cases, because usually they give one question from electromagnetic waves if you analyze the past couple of years. Okay, so hope you enjoyed the class, and make sure you like this video. And if you loved it, then because there were so many interesting applications, just type it in the comments after the lecture, loved it. Just type it out in the comments. Yes, sir, loved it. Okay, thank you. It means a lot. Thank you, Krishna. Bye bye, Madhumati. Have a great time. Yes, bye bye, Evening Star.